So to start off, the agenda for my session today will begin with an introduction to directed energy deposition, because it is the AM process that the different case studies that I'll be showing relies on. Following that, I'll start with my first case study, coloring in with a big crayon, followed by 3+2 additive manufacturing and hybrid manufacturing. Case 3 is coating walls, and finally process parameter development will be my final case study. So what is directed energy deposition in additive manufacturing? So first off, introducing additive manufacturing as defined by ASTM. It is a process that is used to manufacture parts through layer by layer deposition using 3D CAD models. And AM has 7 main categories: binder jetting, material extrusion, material jetting, powder bed fusion, sheet lamination, back polymerization, and last but not least, directed energy deposition. And directed energy deposition is typically used for near net shape parts, for repair parts, and for feature additions. So directed energy deposition uses a direct energy source to melt and fuse deposited materials. And it typically has 4 main types of heat sources. So 4 different types of heat sources can be used with directed energy deposition: laser beams, electron beams, wire arcs, or plasma arcs. And the video to the right here is one by an industrial partner of ours in Italy called Prima Additive. And this video shows their laser dyne 430 machine with a laser head melting and depositing powders onto a substrate. And with DED, there are typically 2 different types of feedstock. You can either have powder feedstock or a wire feedstock. So the image to the left uses powder feedstock, image to the right is a wire feedstock. And your type of feedstock typically depends on the machine that you're using, the availability of the material that you're using in either feedstock, amongst other things. So then the user can choose which feedstock type is appropriate for their application. Moving on to the case studies. Our first case study is titled Coloring in with a Big Crayon. So this is a feature part that we have here that I'll be showcasing on our software. So with our software APlus, we can have 4 different approaches in a single operation to fill in a part. So as opposed to manufacturing simulation, machining simulations, where you can only use one type of approach for one type of operation, we have 4 different types of approaches that can be used in a single operation. And I'll show you how in our software. So here, this is our software, which is an add-on. APlus is our software, which is an add-on to Mastercam. It's a seamless add-on. And this is our feature part on there. So just looking at the part and then going to the parameters, we see the different types of approaches. We have boundary passes, fill passes, void passes, and thin wall passes. So the 4 different types of approaches that can be used. Boundary passes are typically used as boundaries or outlines for a part. Fill passes are used to fill in the interior of a part, and we have fill styles, so different types of fill styles that a user can choose from. Void passes, since DED is like coloring in with a big crayon, so there could be some underfills in a part or some voids in a part that we'd like to go to and fill. And then last but not least, we have thin wall passes, and this is used for when a feature part has thin wall features. So for instance here, these 2 long extensions would be considered for thin wall passes. So if we go, our tool in this example is an 8mm spot size, and the thickness of the thin wall passes that we have is also 8mm. So if we equate the bead width to the spot size, then we'll get an exact single deposition or a single layer for these extensions, as we'll see here. So because we are using an 8mm spot size, in an 8mm location, then it's just one deposition here. So then if we go back, if we'd like to have more stock for machining, then we can change this portion here. So we're not going to equate them. We're going to use a bead width that is a bit narrower than the thickness of the part that we have. So we'll use 7.5 here. And instead, when we regen this part, we'll see that we will actually have two passes instead of just a single pass in these thin wall locations. And this basically gives the user the ability to have more stock for machining. So if a user wants to only have extra stock on these thin wall extensions, this is one way to go about it. As opposed to if the user is satisfied with just the additive finish, then they would have just selected, they would have just equated the bead width to the spot size, and they would have just a single deposition instead of two. So this is for our first case study. Moving on to our second case study, this example here, this feature part here, we call a cup, mainly relies on hybrid manufacturing. And it shows how our software APlus can be utilized for both combining additive manufacturing with subtractive manufacturing, creating hybrid manufacturing. So if we go to our part here, on the software again, the base is just a regular plate that does not need to be additively manufactured. It would be a lot cheaper and more feasible to do this with regular machining, where you would just have a thin plate and drill the holes in it. And then we have the next section, the gray section. We'll go ahead and use additive manufacturing for this part, as we'll see here. So we'll only be starting to deposit this gray section onto the plate that we already have. And as an easier way to show how we merge both additive manufacturing and machining, the next step would actually be to drill in the holes. So, so this would be a lot easier than if we were to have the entire part from a single billet and using regular machining, and have to use a long drill that would actually have to go through the whole height of this part. So it's a lot easier to do one step of additive followed by a step of machining for this specific case. And then followed by this step, we'll go ahead and print the rest of the cup using regular additive. And then we see that we have three bosses, or what we call ears, in this part. And these parts are all part of a single solid. So this whole cup is made using a single solid. So instead of having to create different solids for these added features, our APlus software actually has parameters that can help isolate features on a part without having to create separate solids for them. So if we go to the parameters here, we will be able to see how we have different features that can help us isolate a solid feature. So if we go to toolpath, the first isolating technique would be choosing the correct slicing plane. Followed by that, we have Z limits. So instead of asking to slice the full part, we have Z limits for the part. So here, instead of like slicing the entire part, we're limiting it to 30 to 45. And then we have containment boundaries. So containment boundaries basically has us selecting, we're able to select the chain, and we're telling the software that we only want you to print whatever is within this chain here. So don't build anything else. So by using these three different isolating techniques, we're able to regen a part, and we'll see how we are now only printing this this solid feature without having to create like a separate solid for this boss. So we see here how these isolation techniques enabled us to do that. So this is our second case study using hybrid manufacturing. Our third case study is titled Coating Interior Walls of a Cavity. So this, this feature here shows us how additive manufacturing can be used for coating techniques, as well as printing entire parts or like complete parts, or using repair. Coating surfaces is also another feature that we have that is supported by our software APlus. So if we go to the part here on the software, we see that this interior, the one highlighted by orange, is what we want to coat. So we don't want to print the entire part. We just want to coat the surface here. So if we backplot to look at the coating for this part, we'll see that we're able to, again, isolate this this feature or this coating surface and only print that using our AM surface outline toolpath. And also we can see that another feature that we have is indicating the required side tilt angle that the user would like to use in their feature part. So this allows the laser head or the tool head or the heat source head basically go into different angles and different cavities of a part with more complex features. And then last but not least, our last case study for my session is process parameter and toolpath development. So this this feature here uses AM outline. AM outline is a toolpath that we have that would allow users to be specific in the sequence of deposition that they would like to have for their part. So if we look at these same sets of triangles here, the image to the right shows the order of which each part is being deposited. And this order is really up to the user to select. And I'll go to the software and show you how that is done. So if we go here, this is our part again with different triangles inside one another. And if we go to our part model, we can just see the different layers that we hypothetically would like to print. So then after that, if we go to our parameters, we can see where we can select the sequence of printing that we'd like to have. So we go to our selected chains. These are all the chains involved in the printing of this part. So if we go to one of the chains, chain 19, you find that it becomes highlighted with yellow, chain 20, chain 21. So this is just the sequence that I have, or the order that I have for printing this part. And this sequence can be changed based on what the user would like to have. So this can be very useful for experimental cases for the user, knowing how much heat is going through the part, if they deposit one way as opposed to the other, things like that. And this is actually supported by one of our researchers, Beta, from our R&D team. She works on junction structures and deposition sequences to understand the metallurgical effect that that deposition sequences can have on different parts. And she's actually part of our panel discussion happening today at 2:30 p.m., where she'll be one of the researchers talking more about her her work. And we use, or we intend to use, like findings from our R&D team to incorporate within our software APlus.